Thought I would do another counting example from section 9.3. So this is actually exercise number 39 from that section. And we're just going to practice using the concepts from this section to get an accurate count. How many integers from 1 to 999,999 contain each of the digits 1, 2, and 3 at least once? Okay, so the hint is that for each of those numbers, 1, 2, and 3, let's define a particular set of integers in that range that do not contain the digit I. Let me write out their hint carefully. So A1 is going to be the set of integers from 1 to 99999 that do not have the digit 1 in them. So something like 9700000. That would be such an integer that does not contain the digit 1. And I'm going to do the same thing for A2 and A3. And then let's go ahead and let S be the set of all integers from 1 to 999,999. All right, so let me draw a little Venn diagram to show the situation here. Let's say S is sort of the universal set. It's all of the numbers from 1 to 999,999. How many are there in the set S? It's worth noting here that that is simply 999,999, many numbers, or N of S. And then you have some of those integers, A1, that don't have any ones in them, right? No ones. There is a set A2 that has all those numbers between 1 and 999 that do not have the digit 2. But keep in mind, there are plenty of integers that have neither the digit 1 nor the digit 2, like this 970,000, for example. So A2 has no 2's. And then finally, the set A3 is the integers that don't have any 3's in them. Okay, and the Venn diagram I've drawn is descriptive because you do have numbers in each of the segments of this Venn diagram that I've drawn. And the count that I'm actually looking for, those numbers that have each of 1, 2, and 3 at least once, is out here, basically. If you are an integer that has each of 1, 2, and 3 represented at some point, then you are not in A2, nor are you in A1, nor are you in A3. It means you don't not have a 2 or something like that, a double negative there, and you realize that this is the count that I want out here. Okay, so what I really want to do is compute the number of elements in the entire set minus A1 union A2 union A3. Okay, and from the difference rule, I know that that's simply the count in S minus this count. And because of the addition rule that we've just developed in this section, I can write this out. Okay, so there you have it. If I can just count each of these individual terms, then I can get the answer to the question. All right, well, we already know NS. Let's do some of the other counts. How many integers are in A1, for example? Well, let's kind of get a drawing so I can help do like a multiplication rule count for the integers that fall into A1. So I'm trying to think of all the numbers I can construct with the digits from 1 to 9 that do not have the digit 1 in them. So I guess I'm constructing numbers that have, well, they could have 0s, 2s, 3s, 4s, 5s, anything up to 9, right? So I can make a sequence of decisions about how that number is constructed. I've got basically 9 possibilities of numbers that I could put in the very first slot. So I'm imagining this is like the 100,000th place. I could put a 9, 8, 7, 6, 5, 4, 3, 2, or I could put a 0 there. Putting a 0 there would be like, representing a number like 500. I can imagine 500 as being 000 Got it? So I do have 9 choices for the first slot. And similarly, I have 9 choices for the second, the third, the fourth, the fifth. And then when I get down over here, I don't have the choice. Oh, I have to be careful about this. So when I get down to this last decision, it gets a little bit tricky. So I'm going to try and think about this carefully. If all of these other numbers here were 0, then I don't have a choice to put 0 here, because that would give me 6 zeros, which is representing the number 0, which is not in between 1 and 999. But otherwise, if there's any non-zero choice that's been made there, then I can put a 0 there, right? Like 500. What I'm going to do is I'm just going to pretend like I always have the choice to put the number 0, and I think about this count right here. This is the count 9 times 9 times 9 times 9 times 9 times 9. That is all of the integers from 0 to 999,999 that don't have the number 1 in them. So that's going to be a bit of an overcount. 9 times 9 times 9 times 9 times 9 times 9 minus the number 0000000, which is representing the number 0. Okay, so let me compute that. Okay, and just observe that this is going to be exactly the same count for A2 and A3, because excluding 1 from the construction of the number is the same thing as, count-wise, omitting 2 or omitting 3. So this is the count for A2, and it's also the count for A3. Okay, now we have that logic established, we can get these other counts as well. So let's try and count up all of the integers that don't have any 1s and don't have any 2s. Well, I go through this decision process, and for the first slot, I'm not allowed to put a 1 or a 2, but I could put a 0, 3, 4, 5, 6, 7, 8, 9. So that is 8 choices all the way down to 8 choices there. But again, I allowed 6 zeros, so I have to subtract that count. So that's going to be 8 to the power 6. And then finally, and that's going to be, of course, the same as the other pairs. And finally, I get my intersection of all 3. I'm counting the numbers that don't have a 1, don't have a 2, and don't have a 3. That's going to be 7 to the 6th minus 1. So I could just put all these pieces together and get the answer to the question. Okay, so there you have it. I got 74,460, and you can see in this counting exercise, we got to use the addition principle for 3 sets, as well as the set difference principle.